Hello friends, welcome back. Let us resume our discussion on the second law of thermodynamics. So far we have been looking into the different laws of thermodynamics, and by way of looking into these laws we got exposed to several thermodynamic variables. We refreshed our understanding or the introduction of several thermodynamics variables. Now in addition to that, we are in a position to state how for a given spontaneous reaction, for a given irreversible reaction, these thermodynamic variables will vary. So we got exposed to different thermodynamic variables, and we saw that for a given spontaneous reaction, for a given thermodynamic reaction, for a reaction that occurs in nature on its own, how these thermodynamic variables would vary. So based on this understanding, we postulated, or there's been certain laws that has been postulated that acts as the criteria to decide if a given reaction is either spontaneous, reversible or not. So after understanding what these different variables mean and what are their role in a system, how to describe their role in a system, we use to relate these variables to both reversible and irreversible reaction, both spontaneous reaction that occurs in nature on its own, and other forms of reaction which is reversible in nature, which can go back to its initial state without any input from the surroundings. Now, after describing these two sets of reaction in the framework of the second law of thermodynamics, we saw that these reaction, they exhibit, or because of this reaction, as a consequence of this reaction, the thermodynamic variables to which we got ourselves exposed to, they vary in a specific way, and this specific variation, this specific change of the thermodynamic variables in relation to these different reactions enabled us to constitute certain criteria that helped us categorize a given reaction. So these criteria will help us categorize a given reaction as spontaneous reaction, or irreversible reaction, or the system is not undergoing any reaction, or the system is in a static state. So this we saw in our previous lecture, and one variable that is pivotal in enabling us to understand the nature of the dynamic system is the change in the entropy. So this change in the entropy, which we refer to it as, generally we refer to it as the entropy, we refer to it as S, and this delta S is the change in the entropy. So depending on, whenever you are looking into or studying a dynamic system, depending on how this change in the entropy is when the system changes, we will be able to then definitively state what is the nature of the change in the state of the system. Supposing if the change in the state of the system is associated with not much change or absolutely no change in the entropy of the system, then the overall change in the entropy of the system is zero, even though the system is exhibiting some change in state. Then such change we refer to it as, or such change can be categorized as a reversible change. So reversible change using a thermodynamic variable, particularly entropy, can be defined as a change where there is no ultimate difference in, or there is no ultimate addition or decrease in the entropy of the system. The same way, when there is a continual increase in the entropy, then we would refer to that such change, a change that would render a continual increase in the entropy, such system that is that ultimately increases, that keeps on increasing in entropy, such changes that is exhibited by the system, we refer to that as an irreversible or a spontaneous change. So these changes are they are governed by, without any external impulses, they are governed by this by the system is naturally on its own moving from a high energy or unstable state to a new stable state. So depending on how this particular thermodynamic variable varies, we are now in a position to describe a dynamic state of the system. So initially, if you could recollect, our purpose of studying the second law of thermodynamics was to understand the dynamic state of the system, and by virtue of this particular thermodynamic variable, that is entropy, now we are in a position to state, by considering how this particular thermodynamic variable varies, we are in a position to state what is the dynamic change that is exhibited by the system. If it is zero, it is a reversible change, meaning if there is no change in the entropy associated with the system, then whatever changes that the system is exhibiting is a reversible change. On the other hand, if because of the changes that the system exhibits, there is a continual increase in the entropy, then in that case, the system is exhibiting an irreversible change. The system is moving from an unstable state to a stable state. And if you consider purely from a mathematical standpoint, there is no possibility, there is no way we could have a change in the state of the system when the entropy is decreasing. So this is not possible, or this is rather physically not possible in a system. So we cannot have a system wherein there is the entropy of the system decreases while the system is changing its state. So this is not confined, this particular law. So this is one version of the second law of thermodynamics, and this second law of thermodynamics, it is not confined to any particular system. So this is rather universal, this is rather a generalized version of the second law of thermodynamics. You can either have the change in the entropy to be zero, we can either have a null change in the entropy, or we can have an increase in the entropy. We can never have a decrease in the entropy. If there is a decrease in the entropy, then it is not a physical system, and such system is not thermodynamically coherent, and it cannot be found in the physical world. So such is the importance of, such is the gravitas of this particular second law of thermodynamics. Now, the reason we want to branch away from the second law of thermodynamics is primarily because, so how much ever the second law of thermodynamics is important, how much ever the entropy, the role of entropy is important in determining the nature or the state of a dynamic system, it is not straightforward to calculate or estimate the change in the entropy in a physical system. So therefore, these criteria need to be formulated, or rather reformulated in such a way that we are able to access the thermodynamic variable in a physical setup. So let me repeat, even though we have arrived at a wonderful set of criteria that helps us understand, that helps us describe the dynamic state of the system, this particular variable, that is entropy, calculating the change in the entropy alone in a physical system is not that straightforward. So therefore, we need to have the similar criteria that are based on accessible variables, the variables that can be measured in the physical system. So therefore, we are spending some time, we are dwelling on the second law of thermodynamics. We are attempting to reformulate the second law of thermodynamics based on variables that are accessible to us, that are measurable by us. So that is what we will be pursuing in the upcoming couple of lectures, or even more than that. So in order to do that, as a starting point for it, let us now begin with, let us now continue where we left off in the previous lecture. That is, we began by considering the change in the entropy, not of the system alone, or not of the surrounding alone, but the overall change in the entropy. Now, when you consider the expression for the overall change in the entropy, it is nothing but the change in the entropy of the system plus the change in the entropy of the surrounding. So essentially, while during the introductory lectures, we saw that when you want to focus on a given system, we need an area of an universe, we need an area of a given setting that is separated from other areas. So we need to have an area of focus. So this area of focus is rather separated from its surrounding, from its other environment by a layer, and this layer we refer to it as boundaries. So a boundary is what creates a system, and anything that is away from the boundary, that is not encompassed or enclosed by the boundary, will come under surrounding. So essentially, the whole universe we can rather to consider rather to take a view from to take a cosmological view rather. So what you essentially have is the whole universe can be separated into surrounding and the system, and the system is is distinguished by a boundary, and whatever else is there in the universe can be treated as surroundings. Of course, this is just a view that that includes the entire cosmology. Now, when you have such an expression, now it is possible for us to understand, or it is possible for us to see how the particular criteria that we have considered on the criteria that dictates how a dynamic system should vary will be associated with the entropy, the change in the entropy of the system and the change in the entropy of the surrounding. Now, when we consider the second law of thermodynamics, when we were focused on this discussion here, we were exclusively talking in terms of system. We were talking in terms of the entropy change that is associated with the system rather, and the change in the state of the system that is responsible for this entropy change. So what we essentially consider while discussing in the framework of second law of thermodynamics is, we assume the system is undergoing a change. In response to this change, as a consequence of this change, there is a change in the entropy, and based on this change in the entropy, we are then describing a criteria. Now, instead of considering the system, now we are expanding our focus. We are considering rather a universal view, and here we need to include the change in the entropy of the surrounding. So for that, we need to understand the changes in the thermodynamic variables that are associated with the surrounding in relation to that of the system. Now, we arrived at this relation here, that is, during an irreversible reaction, there should be continual increase in the entropy of the system by considering the expression that rendered us the reversible criteria. We arrived at this criteria for the irreversible reaction, for the irreversible change in the state of the system, by beginning with the criteria that is associated with the reversible change. So, in case of a reversible change, the change in the entropy should be zero. That is, whatever change is introduced in the system is rather reversed by it during the dynamic processes. So it means when we quantify this change as delta Q in, so you are feeding in a specific heat input at temperature T, and a specific amount of heat is rather removed at a specific temperature, and since it is removed, we have a negative sign here, and the summation of these two is 0. So this is nothing but the overall change in the entropy of the system is 0. So now when you want to introduce an irreversibility to it, what you would essentially do is we need to disturb this balance here, and in order to disturb this balance, we add certain component to it, certain component to this expression, and this certain component can be just one or many, and this can be referred to as Q bar and T bar. So now we have disturbed this balance of the change, this reversibility of change that we observe in a cyclic process, in a reversible process, and since it is disturbed, it is no longer equal to 0, and this disturbance of the reversibility, this introduction of irreversibility is achieved by this term here, and we saw as this term, and it is rather conceptually we can state that as this term here increases, the degree of irreversibility increases. So when we refer to this term as the entropy of, so essentially what we have now is, we now have a combination of these two terms which can be referred to as the entropy change during the reversible process. So ultimately these two terms here, this one and these two terms here can be referred to as the entropy change during the reversible process, and it is equal to 0. And this term which we included to introduce the irreversibility is the entropy change that introduces the irreversibility. So irreversible change. So entropy change that is associated with the irreversible reaction, and as this particular term increases, then what we are essentially doing is we are increasing the degree of irreversibility. So this term here is positive, therefore we arrive at this criteria here. So only when this term here, the degree of irreversibility that introduces the degree of irreversibility in a reversible reaction increases, then the corresponding irreversible change will also increase. So that is how we arrived at this particular expression here, this particular criteria here, that is an integral part of the second law of thermodynamics. Now we need to arrive at similar expression for the entropy change in the surroundings. Now when you consider the entropy change in the surroundings, for this reversible reaction here, now it is important for us to note that whatever heat input you are feeding into the system is being removed from the surroundings. So therefore the heat input, whatever you are feeding into the system, is it is the same amount of heat is rather removed from the surrounding. So therefore, what essentially we are observing is the heat QIN that is fed into the system is now removed. So this is fed into the system is actually removed from the surrounding. So we are considering the entire universe, whatever whatever may be the boundary of the system does not include will be categorized as the surrounding. So this could be a reservoir, or this could be anything. So whatever is not enclosed by the boundary of the system will be considered as surroundings. So whatever input we feed into the system is similar to that of the removal of heat from that of the surrounding, and whatever heat output the system gives, that would be nothing but the heat that is fed into the system. So whatever Q output is for the system will be Q in for the surroundings. So whatever Q in for the system would be Q out for the surroundings. Now let us stick with these expressions or these terms here, and then try to express the reversible reaction in terms of the entropy of surroundings. And when we do that, the heat input that is fed into the surrounding would be the heat that leaves the system. So whatever heat that leaves the system will be the heat input for the surroundings. So in that case, Q. So this would be the change in the surroundings. So this would be the initial change in the surroundings, because whatever heat, so Q out is the heat that is left of the system. The Q out is the heat that is the output of the system that is left the system, and after leaving the system it enters into the surrounding. So that means Q output is the heat that is entering into the surrounding, that is fed into the surrounding to bring about a change. So this change can be quantified in this manner, the ratio of the heat change to that of the temperature, to the corresponding temperature. And now whatever heat that is fed into the system is nothing but the heat that is removed from the surroundings. So it can be expressed. So the heat that is removed from the surrounding, the heat that moves out of the surrounding into the system, can be expressed in this manner. So whatever heat that is fed into the system is the heat that is removed from the surrounding, and whatever heat that the system gives out is the heat that is fed into the surrounding. And that's the reason why we have this reversed expression for the surroundings when compared to that of the system here. So the blue is for system and the black is for surrounding. Now given that, even though the signs have been reversed, the value of these heat input and the temperature and the heat output and the corresponding temperature remains the same. So therefore this expression here remains balanced, and therefore this criteria remains the same. That is, for a reversible reaction, the change in the entropy of the surrounding is 0. So when you have a reversible reaction, even though these signs get reversed, so whatever heat that is gained by the system is treated as the gained heat that is lost by the surrounding, and whatever heat that is lost by the system is treated as the heat that is gained by the surrounding. Even though this change in the convention occurs, the criteria that is based on entropy, that criteria that dictates or that describes the reversible change remains the same. That is, the overall change in the entropy of the surrounding is 0. So there is no change in the entropy of the surrounding when the process is reversible. Now, in the same way, if you want to introduce a degree of irreversibility, so essentially Q out. So this is how we have described the reversible entropy of the surroundings. So combination of these two here is the reversible entropy, or rather we will make it more clearer. So this is the entropy of the surrounding, and we will have R here, or we will make it R here. So this is the reversible entropy of the surrounding, and we saw that even though we are talking in terms of the surroundings, the entropy change in the surroundings, this will be 0 for a reversible process. So that is what we saw in the previous slide. Now the same way, when we want to introduce a degree of irreversibility, we introduce certain heat change and corresponding, we introduce certain changes that is quantified by the ratio of the heat exchange and the temperature. Now when we do that, similar to that of the surroundings, even though we are talking similar to that of the system, even though we are talking in terms of surroundings, this term here needs to increase in order to increasingly disturb this balance. So this balance is what categorizes, or what characterizes rather, the reversible process, and this additional term here, it needs to increase in order to ensure that this balance is disturbed. Now, only when this keeps on increasing, you will be able to disturb appropriately the balance. So essentially, this is the term that brings about the irreversibility to the surrounding, and this can be referred to as the entropy change in the surrounding that brings about the irreversible change. So the entropy change that brings about a reaction in terms of the surrounding, and this should be positive and should be keep on increasing in order to ensure that the degree of irreversibility increases. Now, when you consider a spontaneous reaction, an irreversible reaction, wherein the surrounding moves from an unstable state to a stable state. Now, whenever you have such a consideration that is based on surrounding moving from an unstable state to a stable state, even though the conventions associated with the parameters, certain parameters will get reversed, the criteria, it remains the same. That is, even though we are talking in terms of the surrounding exhibiting an irreversible change, the surrounding moving from an unstable state to stable state, the change in the entropy associated with the surrounding should correspondingly increase. So, irrespective of the system or the surrounding, so the entropy should increase in order to ensure that the system is moving from an unstable state to a stable state. So irrespective of if we are considering in terms of system or even if we are considering in terms of surroundings, the entropy change associated with these two, system or surrounding, should increase when we need to have a spontaneous or an irreversible process. When you have a system changing from unstable state to a stable state, when you have a surrounding changing from unstable state to a stable state, the corresponding change in the entropy should always increase. Now, with this understanding, if you consider the expression for the overall change in the entropy, which is nothing but the change in the entropy that is associated with the system plus the change in the entropy that is associated with the surrounding. Now, since here we saw that even though there is, due to convention, a reversal in the signs of the thermodynamic variable associated with system and surroundings, the criteria remains the same for both system and surrounding. For a spontaneous reaction, a spontaneous change, the entropy should increase. So when you when you take this understanding and place it here and consider it in this framework, in this expression for the overall change in the entropy, then the overall change in the entropy should always increase when we observe or when we consider a irreversible change. So the overall change, one reason for considering the overall change in the entropy is, so this gives us, or this particular term, the overall change in the entropy, is not restricted to a given system or surroundings. So supposing you are talking about some reaction, some change that is occurring in the universe, I don't know, birth of a star, it could be a birth of a star, or it could be a death of a star, whatever it is. It does not need to be confined to the systems that we are interested in, not just the material system, any change in the world. It is difficult at times for us to distinguish the system from that of the surroundings. So in such a case, when you consider the overall change that includes both the system and surrounding, this expression here states that this overall change should also increase when you have a spontaneous or an irreversible process. So that is one reason for considering the overall change in the entropy. We saw that the second law of thermodynamics is rather universal. It is not confined to a specific system, and this second law of thermodynamics, if it is not satisfied, then we do not have a physical system, such as the importance, such as the significance of the second law of thermodynamics. Now, such laws should not be restricted by our description of system and surrounding. Such laws should be rather universal, and this universality of the second law of thermodynamics is achieved by describing this overall change in the entropy. And when you have such overall change in the entropy, that constitutes the change in the system and the change in the surroundings, and we saw that wherever you observe an irreversible process, be it somewhere in the space, be it on Earth, be it in the microscopic scale, be it in the mesoscopic scale, wherever you see a reversible or irreversible change, a system moving from an unstable state to a stable state, whenever you see such a change, even if it is difficult for you to distinguish the system from that of the surroundings, if you calculate the change in the entropy, even if it is difficult for us to exactly distinguish, to exactly identify the boundaries that separate the system from surroundings, if we are able to calculate the change in the entropy, then we would be able to state if such a given change is reversible or irreversible. Because again, even it is possible rather for us as a metallurgist or a material scientist to separate one system, one material from another. A solid from a liquid, it is rather easy for us to separate. But if you take a generalized view, it is not always easy for us to separate a system from that of the surrounding. But what this law gives us, what this expression, which is again a part of the second law of thermodynamics. The second law of thermodynamics is now here expressed in a more generalized manner, gives us as, even if you are not able to rather separate the system from that of the surroundings, even if you are not rather exactly able to identify the boundary, the entropy should always increase when the process is irreversible. So when you see a dynamic system, a system that is changing in state, even if you are not able to separate the system, whenever you see a dynamic change that is happening in the universe, anywhere in the universe, if you are able to calculate or estimate the entropy change associated with it, never mind identifying the boundary, never mind distinguishing it into system and surrounding, you will be able to say if that change is reversible or irreversible if you are able to calculate its change in the entropy. So that is one of the reasons why we need to introduce this concept of the overall change in the entropy that frees us the constraint of the system and surroundings. And this is again, like I said, is a part of the second law of thermodynamics. This is one other version of the second law of thermodynamics which includes both system and surrounding. Now in this lecture we will start from this point, and now let us consume that we are talking, so we will go like progressively. We will begin with considering, now again this is not I don't know, a statistical physics class or generalized class, so this is again we are considering the thermodynamics of materials, so we have to get back to earth after considering the generalities of this expression. We have to get back to earth, we have to focus on the materials, so let us do that. Now the reason we introduced we are discussing in terms of this overall change in the entropy, again we want to arrive at certain thermodynamic variables that is more accessible to us, and therefore we will begin with this expression here. To derive such thermodynamic variables, we will begin with this generalized second law of thermodynamics, the expression that describes the generalized second law of thermodynamics, or second law of thermodynamics in a very generalized or much generalized manner. So now this much generalized expression for the second law of thermodynamics, that expresses the entropy change, the overall entropy change as the sum of system and the entropy change as that of surrounding. So this needs to be greater than 0 when the system is exhibiting a irreversible change. A system is exhibiting a spontaneous change. Now let us, like I said, let us go progressively. Let us consider change in the state of the system where there is not much volume change. So in that case, what we are now considering, we are restricting ourselves to a change in the state of the system, and there is not much volume change that is exhibited by the system. Now when you consider such a case, then if you consider go back to the first law of thermodynamics, your change in the internal energy is expressed as the heat is expressed by relating the heat exchange and the work done. And the conventional way of representing the work done is by considering the change in the volume of the system, or it could also be the change in the volume of the surrounding. And when you have a change in the state where there is not much change in the volume, then essentially what you would end up having is the heat exchange is directly responsible for the change in the internal energy of the system or the surroundings. Now what we have is, we have an expression for the overall change in the entropy that comprises of the change in the entropy of the system and the change in the entropy of the surroundings. Now let us focus on the change in the entropy of the surrounding, which could be expressed as, the expression remains the same for both system and the surrounding. The expression that describes the change in the entropy remains the same for system and surrounding and the overall. So for surrounding, this is expressed as the heat transfer with respect to the surrounding, and a temperature. So let us assume this change is isothermal. So we will make, for this discussion, we will make two assumptions. One is that this change is isothermal. The change that we are focusing on is isothermal, and other assumption is there is no change in the volume of the system or correspondingly the surrounding, because volume needs to be conserved. Yeah. So now we have these two criterions, and because of these two criteria we have arrived at this relation here, and this relation is nothing but, so because of this relation, through this relation, this expression can be written as the change in the entropy of the surrounding is the ratio of change in the internal energy of the surrounding to that of the temperature. Now we saw that in our previous discussion, whatever heat is fed into the system is equal in value but reversed in sign when you discuss it in terms of the surroundings. So whatever heat, if you have a system like this, so whatever heat you feed into the system, so Q is Ys, so Q, this system is the heat if it is fed into the system. When you are considering in terms of the surrounding, the same amount of heat is removed from the surrounding. So if you consider this in terms of the surroundings, there is Q system that is removed from the surroundings. Now when you talk, or when you want to express the change or the heat transfer between system and surroundings, there is only one heat transfer that occurs between system and surrounding, and that is quantified as this particular variable here. When you talk in terms of the system, it is heat gained, so it is positive, and when you talk in terms of the system, it is the heat lost. So if you want to describe the heat, that is the heat change that is associated with the surrounding, it is equal to the negative of the heat change that is fed into the system. So that is what this is the numerical way of expressing it, the changes, the heat exchange that occurs between the system and surrounding. So if you consider this heat exchange between system and surrounding, so you have a specific amount of heat entering into the system, and that we refer to as QSYS, and the heat that is lost by the system is Q surrounding. So since whatever heat that is lost by the system is gained, or whatever heat that is lost by the surrounding is gained by the system, we end up with this relation here. So what we are doing is, we are rather expressing the heat exchange based on that is heat exchange that is experienced by the surrounding in relation to the heat exchange that is experienced by the system. And since this heat exchange is rather one word, a specific amount of heat is lost by the surrounding, and that specific amount, the same amount, is gained by the system. So essentially, whatever in terms of the heat exchange, so in terms of the heat that is lost by the system, since both the values are the same, only because of the convention a sign varies, so therefore we arrive at this expression here. So when you consider a reversal of this process, so the negative of the heat, or the negative of the heat that is lost by the system, is nothing but the heat that is gained by the surroundings. So this expression indicates the heat exchange between the system and the surrounding. So whatever heat that is lost by the system is gained by the surrounding, and whatever heat that is lost by the surrounding is gained by the system, and therefore we have this expression here. And now when we bring this expression to this relation, given that we are restricting ourselves to a change in the state wherein there is no change in the volume, then we can express based on this, we can express for the surrounding the change in the heat exchange to with the surrounding, the heat exchange that is experienced by the surrounding is equal to the change in the internal energy of the surrounding. So this expression here, this generalized expression here, now it is written more specifically, this generalized expression in one, it is written more specifically for surroundings here. Now this term, this expression, or this particular expression here can again be rephrased in such a way that we are replacing the internal change in the internal energy of the system with respect to the change in the internal energy of the or the change in the internal energy of the surrounding. This term here is now, we are looking for a way to replace this particular term here with the change in the internal energy of the system, because we want to have a framework which generally talks about the system. So therefore, we now have the heat exchange that is associated with the surrounding is equal to the internal energy change that is associated with the surrounding. Now similarly, the heat exchange that occurs with the system is similar to that of the internal energy change that is associated with the system. Now we have from this relation that these two are, the magnitude of these two are equal, only the signs vary. So that means we already have derived at this expression which indicates that the magnitude of the heat exchange between system and surrounding is equal, only the signs change. And when you consider these three expressions, that is expression 2, expression 3 and expression 4, you have there is an equivalency between the left hand side of the expression 3 and 4, and the same set on based on this equivalency you can relate the right hand side. So this way you can express the change in the internal energy of the surrounding is equal to the negative of the change in the internal energy of the system. Now what we have done is we have derived an equivalency by considering the heat exchange between system and surrounding, and based on the equivalency and relying on our assumption that there is no change in the volume, and therefore using the expression 1 here we arrived at expression 3 and 4. So we related the heat exchange with the surrounding to the corresponding internal energy change, heat exchange to the system to the corresponding internal energy change of the system. Now since the heat exchange between system and surrounding, there is an equivalency between them, we are exploiting the same equivalency to relate the internal energy change between the surroundings and system, and we have now arrived at this expression here. So the internal energy change between system and surrounding, when you consider the magnitude of it, is equal, only the sign is reversed. Now it is possible for us to substitute now this term here with the internal energy change. The internal energy change of the surrounding can now be replaced with the internal energy change of the system with a negative sign here. So therefore, when you substitute this expression here, it is possible for us to write the change in the entropy of the surrounding is nothing but minus of change in the internal energy of the system and the corresponding temperature. So now we have related the change in the entropy of the surrounding to that of the change in the internal energy of the system by these different sets of equivalencies. So by this set of relation, we are able to relate change in the internal energy or change in the entropy of the surrounding to the change in the internal energy of the system. Now let us go back to our original expression and try to combine all these. Now we will go back to our original expression where we are considering the overall change in the entropy during the irreversible process, and it is the sum of the overall change or the change in the entropy of the system. Now we have related the change in the entropy of the surrounding is equal to minus of the change in the internal energy of the system and the corresponding temperature. So we will write this expression here, change in the internal energy of the system with respect to the temperature here, and this again according to the second law of thermodynamics should be increasing, should be positive and keep on increasing in order to ensure that the spontaneous change progresses. Now we can rewrite this expression as T delta. So essentially we are getting rid of the denominator and expressing in this manner. So again we are carrying over the criteria with us. Now this whole expression, we can by placing this term or making this term positive here, so this change in the internal energy term positive, this whole expression can be written as minus T delta S overall. So we are attempting to make this change in the internal energy of the system positive, so therefore we are bringing the minus sign here and we end up with this expression here. So we have change in the entropy of the system and we have change in the internal energy of the system and the overall change in the entropy. And now when you consider when you relate the second law of the criteria that is based on the second law of thermodynamics to this expression here. Now we saw that the overall change in the entropy should always be positive for a spontaneous or an irreversible reaction, and so this needs to be positive. And the temperature, when it is particularly expressed in Kelvin, then this also will be positive for all physical systems. Now when you have the combination of these two, you ultimately have a positive term. So according to the second law of thermodynamics, this needs to be positive, and according to the given that we are considering temperature in terms of Kelvin, so this term needs to be positive, and both these terms, the combination of these two alone needs to be positive. However, we have a negative sign here. So there is a negative sign here. So therefore, this whole term becomes negative. And when we have this term becoming negative, what it means is that this criteria, because of the presence of the negative sign, it means it gets reversed. So the criteria is the entropy, the overall change in the entropy should always be positive for a spontaneous or an irreversible change. When a system is moving to its stable state, then the entropy, the corresponding entropy change should always be increasing. It should be positive and always be increasing. Now we have the entropy preceded by a negative sign. So that means this criteria gets reversed. So because of this negative sign, this change in this term here should be less than 0. The second law of thermodynamics, the criteria associated with this second law of thermodynamics states that this criteria, so because of that criteria, this negative and the negative sign associated with this term, it means that minus T delta S, the overall change in the entropy, should be less than 0, and this now becomes our criteria for the spontaneous or irreversible change. So because of this negative sign here, now the whole criteria has changed. So this should be less than 0. So this should decrease for this particular term. Because of the negative sign here, the overall this overall term should decrease in order for the spontaneous change to proceed. Now when you substitute that criteria here, so when you, instead of considering the left hand side of the expression alone, when you consider the same criteria, impose the same criteria for the right hand side of the expression, we end up with a criteria that states that this change T delta S system, this change, this particular expression, this particular combination of terms, this particular relation should decrease when there is a spontaneous or an irreversible change that is exhibited by the system. So based on the second law of thermodynamics and considering that there is a negative sign here, we saw that this particular term should decrease for an irreversible change. And since this term is equal to the combination of these two terms here, so the same criteria applies. So this combination of these two terms should also decrease when the system is experiencing an irreversible or a spontaneous change. So this expression here, that is change in the internal energy of the system minus the product of temperature and change in the entropy of the system, should decrease for a spontaneous or an irreversible change. So this is the criteria again that is based on the second law of thermodynamics, and we have arrived at by certain consideration. Now this expression can be written as, so delta U can be written as the difference between the final and the initial state. The same goes for the change in the entropy of the system, which is the difference between the entropy of the difference in the entropy between, or the difference in the entropy between the final and the initial state. So if you substitute these, you end up with this expression that U2 minus U1 minus T of should be less than 0, and it should be decreasing. So when we have a spontaneous or an irreversible change. So this can be manipulated, this expression can be rewritten in such a way that U2 minus T S2 minus U1 minus T S1 should be less than 0 for a spontaneous or an irreversible change to occur. So this criteria needs to be satisfied for a spontaneous or an irreversible change to occur. And again, when we can manipulate it further, U2 minus T S2, U1 minus T S1. So when this criteria is satisfied, if and only if this criteria is satisfied, then it is possible for a system to experience. So this should be 1, for a system to experience an irreversible change. So what this means is that you have two states. It is possible by considering the internal energy, temperature, entropy, it is possible for us to describe two states of the system. Only when one state of the system is the combination of these variables. So one state of the system described by this combination of these variables is less than the other state of the system, then there is a possibility. Only if this is satisfied, there is a spontaneous change that is possible. So if we replace this combination of these terms as A2 and A1, only when the value of A2 is less than the value of A1, a spontaneous change is possible between state 1 to state 2. And this term A, which is nothing but the combination of the internal energy and entropy, is what we refer to as the Helmholtz free energy. So essentially, by beginning with the second law of thermodynamics, we have described or we have defined what an Helmholtz free energy is, and based on the relation between the Helmholtz free energy, now we are able to arrive at a criteria for an irreversible reaction. And that criteria states that only when the Helmholtz free energy of a given state is less than that of any other state, a spontaneous reaction is possible. Supposing you need to have a change in the state of the system, you need to have a system moving from the unstable state to a stable state, the Helmholtz free energy of the stable state should be less than that of the Helmholtz free energy of the unstable state. Only then you can describe that as the unstable and the stable state, and only then the spontaneous change is possible. So now, based on the second law of thermodynamics, we have arrived at a criteria that is based on the combination of certain variables, and ultimately that is based on the Helmholtz free energy. So according to this expression here, the system, when we say a system moves from unstable state to stable state, what we are essentially stating is the system moves from higher Helmholtz free energy to the lower Helmholtz free energy. So what we have now done is we have expressed the criteria that is based on the entropy. So when we consider the second law of thermodynamics alone, it is exclusively based on entropy. Now we have described it in terms of Helmholtz free energy. The unstable state is the one with higher Helmholtz free energy, and the stable state is the one with lower Helmholtz free energy. Now, when you have such a system with a higher Helmholtz free energy and a possible state with lower Helmholtz free energy, then a spontaneous and an irreversible change is possible. So with this description of the second law of thermodynamics, with this criteria for the irreversible change based on Helmholtz free energy, I will wind this lecture up. We will build on this. We will try to gain more understanding of this criteria in the subsequent lecture. Goodbye.